I went ahead and started recording.
Awesome. Okay, welcome everybody to the CSCA48 review seminar for the midterm. I'm Katrina Best. I'm a representative, or the ComSci representative at AMAX. Tabeeb, do you want to introduce yourself?
Yeah, so I'm Tabeeb. I'm also another CS representative for AMAX, and I'm also the president of CSEC.
Okay, so we're just going to get started. We've prepared a couple of slides for you. So 1 second. Can everybody see my screen? Awesome. Okay. Yeah, okay. So welcome to our review seminar. First of all, we're going to be going through all these different topics to cover. There is a very high chance that many, if not all of these, will be on your midterm. So make sure that you're paying attention. We're going to go over memory models, pointers, a couple of examples, constructing structs, so creating different functions based on Scratch, and then structs in the memory model, just to make sure that you remember that. And then Tabeeb's going to go over dynamic memory allocation, linked lists, and complexity as well. Tabeeb's also going to be answering the questions in the chat while I present. Right. Okay. So first thing we want to cover, going over the memory model. So I know it's been quite a while since you've probably seen this, but this goes back to Unit 2, and there's a very high chance that this will be on your midterm. So can anybody remember or let me know how to add an integer? Yeah, to the model.
Feel free to turn on your mics as well if you want to answer. Yeah, I think the screen is a little bit cut off.
I might be able to get it out. Hold on. Can you see it now? No, okay.
It's a bit cut off, like the left side of it.
I guess I can, I guess I can share my whole screen and then I can just make it a bit smaller. Does this look better? Yeah? Okay, awesome. Okay, so first one, when we're adding an integer, you first want to make sure that you've got the type, you put the actual data inside of the box, and then you have the variable name in the top left corner. Easy peasy, you guys should remember this. Now adding a char or a character, same sort of thing, except for make sure that you've got single quotes as well, because double quotes means it's a string. So we have S over here, it's a char, and then we've got the variable name. I just chose S as an example. Now adding a string, remember that C doesn't actually have a predefined data type called string, so it just becomes an array of characters. So when we actually add this, it's going to take up several different boxes, probably like consecutively right beside each other. So in this case, I've got HELLO. It still has the variable name, and the type is now char with the actual array size. And don't forget this last special character at the very end, this /0, that counts as one char or one character. Does anybody have any questions? No? Okay. Okay, let me know if you have any questions. I'll try to check the chat. Next thing, so a bit of a review of arrays, and then we're going to go through pointers as well and the difference. So can you have several different data types in one array, in C specifically?
No.
No, you cannot. Exactly. So you can only have one. In Python, I believe you can mix it up. Java, I don't think you can, but C, it's specifically one. So what's wrong with this here?
There's no room for the end line character
Exactly.
or the
Yeah.
/0, whatever it's called, delimiter.
Awesome. Thank you. Yeah. So if we're going through this and it tries to ask that /0, it's not actually going to go and find it. And you might end up getting extra characters or values that are not part of your string. Yeah. What is the difference between an index value and a dereference value in an array? It's kind of a trick question. There is no difference. They are the exact same thing. So there's still going to be the value at that position, whatever it is in the array.
Dereferenced and dropping there.
Pardon?
Oh, sorry, that's an accident.
Oh, okay, okay. Dereferenced. Now I'm trying to remember how I was starting it off. Index value is when it's actually being there. The reference value, honestly, I'm not really sure what I meant by that. You can disregard that though. Okay, what is wrong with this code? There are several different problems with this. So yeah, Ethan, you've got the whole squad there. It looks awesome.
Okay. The first, there's one you're saying P1 equals A as a string. That should be a character.
Awesome. Yep. Yep. So first one, oh, right. Okay. First one, it should be a char. There should be single quotes.
Oh, yeah.
No return statement. That's also another one. There are actually 6 different ones in here.
P is a pointer, not a string. So we're trying to print P, and it's a pointer. We're doing the same thing. The char B equals B as a string as well. That's a problem. And then we're also doing the same thing, trying to print P again as a string when it's a pointer, and it's not.
Awesome. Yes. Yes. Exactly. So actually, Billy, that's okay if you define the string at the beginning. So if you just had char A with like the 2 square brackets, then you would have to specify the amount or how big it is. But if it does have like an actual string attached to it, it's okay. For void functions, you do not need a return statement. Or if you want to return early, you can just say return instead of actually saying like return 0. For this one, yes, I should have added return 0. So I'll just go through them. I only had 5, but you guys caught on like to some of the mistakes that I also did, so that was really good. So first one, actually, we can't do P at position 1. We should actually add P plus 1. So remember the memory address? When it's a string, it's going to be consecutive. So you add 1 to get the position right beside it. So the E in this case for hello. And then we're going to access the actual value where this address is pointing. Then we're going to change it to A. So Ethan, great job. We're going to change it to a char, not a string. Char B should also be just like instead of actually just having single or double quotes, we should have single quotes. And it should be a char C, yeah, instead of a string. The first one's okay though. The first one, P is still a string. However, P is actually a pointer. So it's going to give out an address instead. So we want to actually reference what P is pointing to. And yeah, that last one, we want to do the return one here. Indexing using the pointer again. If you do this, I don't know if it works. I tried it and it didn't work. Tabeeb, could you speak on this one? I don't think it would work.
It's yeah. So you don't know the. I think it could work actually. Yeah, you should be able to. You should be able to dereference like that. Have like one.
Okay. Okay. Never mind then. Sorry about that. But do try to use the pointer format. Yeah. Oh, what else was the? Yeah, the star P or the pointer P, that should be in the print statement so that you're accessing what the address is actually pointing to, not just the address. Yes, yes. Yeah. And in that second printf, it'll actually just be a B. Yes, this is being recorded. And it'll be posted on the AMAX Discord. Yeah, okay. Okay, so next one is going to be the review of pointers. Okay. So what data do pointers hold? I kind of gave this away a little bit, but yeah, we can give that to you. Yeah, host addresses, awesome. What do you need to do when you first initialize a pointer? Good practice. Awesome, yep. Initialize it to null. Yeah, okay. What is the difference between the pointer P times 5 and asterisk brackets P times 5?
One will multiply its value by 5. The other will point to somewhere 5 times farther away, which is probably going to mess up since it's some horrible hex value.
Perfect. Yep. So the first one is actually going to multiply the value by 5. So wherever the address is, you get that value and then you multiply it by 5. And then P times 5, P is actually the memory address. So you're multiplying the address by 5 and then referencing whatever that address is pointing to, not the original one. And that's bad practice because you're losing your original data. Awesome. Okay. Yeah. Here is also the Discord link. It'll expire in 7 days though. Okay, a little bit more review. How do pointers work with an array?
Points to the first value in the array.
Yeah, awesome. Okay. How do you make the pointer's value its neighbor's value? Yeah.
Add
Aaliyah's
one.
got it. Yeah, just add 1. So I actually typed it out, but yeah. Awesome. Okay, you guys have got this. So these are some common mistakes that we found with pointers. So one of them, I think, can you see this? Or is it a little bit out of screen?
Your taskbar is like cutting it off a little bit.
Let me try getting out of this then. Okay, so we can just go through here. So for here, uninitialized pointer, if we just set this pointer to, like we just create it, we don't know what's actually in that pointer. So it could be pointing to some extremely valuable data that, let's say, starts up the OS system, right? And then if you assign that to the integer 3, we don't know where it's pointing, so you're going to get an error here. Another one right here. So let's say we are initiating this double P. We set it equal to 5, and then we free it. And then if we try to set it again, you're going to get an error because P has already been freed. That memory has been let go, so you can't assign it anything else. If you put the free like afterwards, you can totally do that, but before, P is now gone basically. And then last but not least, this memory leak. So char P, we give it some memory the size of 1 char. We copy the value hello to it, we print it, and then we create a new string. We just call it world. And then here, we are assigning P to a new value, A at position 0. This is bad practice because now that string value hello can never be accessed again. And while your computer, like it's very small, like a very small amount of space at the beginning, it's still going to be like, it's bad practice.
A10, not
Pardon?
10.
Yes, sorry, this is supposed to be A10. Thank you, sorry. But yes, and then you can also print it to just double check. I also have this constructing structs example. So this is one with a receipt. And remember back to the analogy of the bento box. So you have this this struct that you've created. For me, I created one with an ID. We've got a string date, amount, tax, the buyer, and the store name. Okay. And then in main, there are 2 differences between using an actual, like the actual data type or a pointer to that data type. So when you first create just the data type receipt, you can automatically start initializing all the values. But for a pointer, you want to make sure that you allocate some space. And if you use calloc, then it'll all be initialized to 0. But Tabeeb will go into more detail about that later. And when you're also referencing the different values for either the actual data type, you use periods. But when you're referencing it with pointers, you want to make sure that you use this arrow instead. Otherwise, you'll get an error saying that that doesn't exist. Does anybody have any questions about this so far? I know I might be moving a little bit fast. No? Okay. Okay, I'll keep going. Yes, you will have access to these slides. I can also, yeah, okay. We'll post them and I'll also put the link in the chat as well, in case anybody wants to look at them. Just to follow along. Okay. Next one, we have another example from Unit 3, I believe. So we included all these libraries. We've got this restaurant score, or this restaurant review, basically. It's just got 3 simple different components to it. So we have restaurant name, restaurant address, and a score. 2 strings and an integer. And then in main, we define review. We initialize it, and that's about it. But how will this look in the memory model? So this is important to remember. You need to make sure that it's all in one box. So this is called a compound data type, where it's all in one box. Even though there are strings in it, it's not looking at other boxes. It's all compartmentalized into this one. And yes, this includes either strings or arrays. They're basically the same thing, just strings are specific to chars. And the data type is whatever you have made it to be, like when you created your own data type. That's the name of it, and you still need the name of it. Does anybody have any questions? Yes, you still can mutate the string. Yes. I think I kind of went fast. Tabeeb, what are you thinking? That's all my asides.
Okay. Do we want to take a little 5-minute break before we continue on with the linked lists portion and complexity?
Yep. I'm gonna go over the question in the chat. But yeah, everybody take a 5 to 10 minute break. We will be back shortly.
Okay. Let's regroup at 8:06.
We just started. We don't need a break.
It's half an hour in.
I know, I went fast. Sorry.
What
Yeah,
are the
so
other topics that are going to be covered?
we're going to be covering dynamic allocation. What else? Linked lists, which will be probably the main focus of the midterm, as well as complexities, which I think you guys have just learned.
Thank you.
No worries. And yeah, Aaron, did that answer your question? They kind of said it already in the chat. Okay, awesome.
So you do card 10 is equal to my string. Okay, so in the memory model, you would normally have something like the boxes set up for my string. Okay. So this is if you did not use dynamic memory allocation, right? So without dynamic allocation. So what happens is if you're in a function, for example, so like you do this inside of a function, as soon as you exit the function, what happens to this block? Do you guys remember?
Disappears.
Yeah, exactly. So as soon as you exit the function, so you return, all this space that got allocated for my string, it would just disappear. So this is without dynamic memory allocation. However, if you have instead, you do, you allocate, so you do like something like this, calloc, and then 10 size of char. Okay, and then, so when you do that, you have to do as, oh, I didn't even give it a variable name. So let's call it S. So you'd have to do str cpy and then your string. So my string. Okay. And then that, what it would do is it would create this.
You use string copy. Sorry, do you need to put the dash or the /0 at the end, or
Oh.
would it do that automatically?
Oh no, you do. That's right. You don't need it. It'll do it automatically. Yeah. So yeah, the difference now is that now if you have this in a function, this data in the memory, it will persist once you exit the function. So what you have to do is, if you actually want to deallocate, you have to call free on the dynamically allocated variable. Okay, so that's calloc. Okay, so you might have seen like calloc and malloc. So I just want to I covered this in my tutorial. I don't know if every tutorial covered it, but like the difference between these two is that calloc will zero initialize an array. So like if you have an integer array, if you do calloc, it will zero initialize it like this. So you'll just have a bunch of zeros. So this is calloc. Malloc, on the other hand, if you ever use that, which you might use in B09, I don't know if you have to use an A48, but it will not actually zero initialize the array. It'll give you a bunch of question marks like this. Okay. And so this is a little bit faster if you don't want to zero initialize. However, if you want to zero initialize, this is a little bit faster. Because if you want to zero initialize while using malloc, you have to do malloc, and then you have to do an extra operation, right, to set everything to zero. Yeah, this is like basically like garbage values. Okay, so that's like the difference between, so for characters, it will initialize to the empty characters. So that's the difference between calloc and malloc. I don't want to go too in depth into it because I don't think it's too necessary to know. As long as you know calloc, I think it'll be fine. But that's just like, just wanted to show the difference between those two. Okay. So yeah, any other questions about dynamic memory allocation before we move on to linked lists? And also, like, I'll say it again at the end, but my office hours are Friday at 2 p.m. online. So you can find that on Piazza, the Zoom link. So if you have any last minute questions before the exam, I think exam is 12th. Okay, so my office hours are before that. So you can ask me last minute questions if you have any. Okay, so let's move on to linked lists then. Okay, so linked lists are a pretty simple data structure. So you have a struct, and then you have some kind of data, whether that be a string, an integer, or another struct within the struct, and then you have a pointer to a next. So this is like a singly linked list. You have a pointer to a next, which points to another linked list node. You can have doubly linked lists as well. You can keep track of like the head or the tail and stuff like that, but this is a very simple rudimentary example. And what we're going to go over for linked lists is we're going to go over a question from the A48 midterm from a few years ago. But before that, so this is kind of, so I've changed it up a little bit, but this is basically kind of like what the question was on the 2020 midterm. So you have this list node struct. So this is a linked list node. It's just a traditional like linked list with your next pointer, which points to another list node. However, inside it, you have another struct, which is this item. Okay, so you actually have a pointer to a struct item, and this is what the struct item looks like. Okay, so item, it has a name, and it has a weight. Yeah, it has a weight. Okay, so that's pretty much it. So we're going to be working with this linked list for the rest of the problems. But first, to get an understanding of how this linked list works, we're going to go over drawing the memory model for the following code. Okay, so what this code is doing is basically you're dynamically allocating some memory for the ABC pointers. And then so these are all items. And then you're setting the name to first, the weight to 50. And then for B, you're setting the name to second, weight to 40, and then a third and 30 for C. Okay. And then what you're doing is you're initializing some list nodes, again with calloc. And then for the first node, you are setting the item equal to that A that you allocated, setting the item for the second one to the B that you allocated, and the third to the C that you allocated. Okay, and then you're setting the next. So it's so yeah, it should be pretty straightforward. I'll give you guys some time to think about how to do the memory model for this. And then we'll take it up together. Okay, so I'll give you guys like maybe, I'll give you guys like 4 minutes to just try to think of some initial ideas. You don't have to like totally finish. If you can't, that's fine. We'll go over it together. But I'll just give you guys some time to work on it. Okay. We'll post the recording on the Emacs server, and I'll also post it on Piazza. So just think about like how many, yeah, exactly. The locker thingies, like how many boxes do you think you'll need to represent all these things? Okay. I think that's like the biggest thing. Well, I guess that's a little vague. What do you mean by boxes? Yeah, there's going to be a lot of boxes. Yeah, 6 boxes. Okay. Seven with the return. Yeah, sure. You can include the return value with main as well. I think during an exam, during the exam, you should probably ask the TA if you need to include the return or not, if it doesn't say for main. But I think to be safe, like you should. Yeah.
Yeah, I guess one way to look at it, what Jacob's saying is that if it says void main, then maybe return is just null.
Yeah.
But if it has integer, you need to make sure it's returning 0.
Okay. Yeah. So for sure, like if it's asking specifically for like the main function, then you probably want to return 0. Yeah. Make a reasonable assumption.
Throw back to last year.
It will return 0 by default. So like if you don't have a return statement on the main, it will show 0.
But you might lose marks for that on the midterm if you don't clarify that in the memory model.
Yeah, I guess just to be safe, like try to be as granular as you can with the memory model diagrams. Okay, so I think we should probably start taking it up. So I'm going to make some space here. And okay. Okay, so we have item A, B, and C. So what we can do is we can actually create those item nodes. Okay. Make it bigger. So we can have the item nodes, and then also the item will have a weight and a name on it. So you can have some. So okay, this is for item, and then list node will also have a. It will have a memory address pointing to the item, as well as a next address. So I'm going to go ahead and copy these. We will need a lot of these. And as someone said, we will need 6 of these. Okay. And then, so let's do this part. So first, let's actually do the items. So item, we can say that this is going to be, so I guess we can do like random locker numbers. So we can say that this is 100, this is 200, this is 300. And this is 600, like that. And then we can say that this is, so this is for, I'll just write here that this is for A and this is for B and this is for C. This is for first, second, third. However, we're going to need more boxes than just these ones. So I'll show you the other boxes we also need. So let's start by just setting these boxes first. So for the first box, we're going to have, so this is for A. A's name is going to be first. So I'm just going to abbreviate it and just have the string here. Normally, you would represent strings with the separate boxes as character boxes, but I'm just going to go ahead and condense it into this one box for the sake of time. So you have, this is a character. We're going to call this the name. Okay. I'm going to go ahead and copy that over to these ones too. So you want to specify the type as well as the name of the variable, right? Try to be as granular as you can.
Tabeeb.
Yeah.
Some people in the chat are saying that it's a pointer, and I think it's supposed to be pointing to another thing.
Yeah. So for the first one, so a name, right? The name. Yeah. So the name. So what it actually will look like in the memory model, like, is you'll have something like this. So this is over here. You'll have something like this. It'll point to, so this is what it will point to. name. This is what it will actually like look like. So it will, when it'll point to this first character over here. Okay. So this is actually not like a string. It's like one individual character. And so that'll, and then from that individual character pointer, you can like add to it to reference the other boxes. Yeah. Yeah, so A should be a box on the stack with address that points dynamic. Yeah, exactly. Exactly. So I was going to add those boxes too. So like, since you mentioned it here, I'll just go ahead and do that here. So you will have, so this is for A. And we can say that this is like memory address 0. And this will point to 100. So that's the first box over here. Okay, and then I'll make a one for B and C. And also, we will also have, since we're also allocating the list nodes, right? So we need one for those as well. So we have B, C, first, second, and third. Okay. Yeah. So you can go ahead and change these to like different numbers as well. 40, 50. This is going to be 200. This is going to be 300, 400, 500, 600. And also, yeah, so you will get a template. So you don't have to worry too much about these things. But so these are item boxes, right? So these are going to be type item. You can put those there. And then these are item pointers. Oops. Copy those. So A, B, and C are item pointers. And then first, second, third are going to be, I'm going to remove these now. These are going to be list nodes. Okay. And then these are going to be, you might have guessed it, are going to be list node pointers. Okay. Okay. So far, so good. Okay. So what's next is, so as you can see, we have these, and then what we also need is okay, so the weights as well. So we can add those. So the first one is going to be 50. It's going to be 40. It's going to be 30. Okay. And then we have, this is going to be integer weight. Okay. So make this smaller. Copy that. All right, so these are the weights. Right, and then finally, we are at the list node. So far, oh, I should add these as well. So again, if I want it to be granular, like fully granular, I would actually make like individual boxes like this for the name, but I'm just condensing it down into the string. Okay, so I also made that note in the slides as well. Okay, so are we good with the item allocation? Okay, so item allocation is looking good. So now we're going to go into the list nodes. So the list nodes, all they're going to do is they're going to store the item. Okay. Oops. It's going to actually store a pointer to the item. So the actual memory box where the item is. So here, it's going to store the memory address of A. So that's going to be 100. Okay. And let's say this is item star. Item. Okay, and make that smaller. Copy that over here. Okay, and similarly, this is going to be 200 for the second one. This is going to be 300 for the third one. Okay. It's the actual memory box, the locker number, right? Because it's a pointer, so it should be the actual memory box. Okay. And then finally, the last boxes here, these are the next pointers. So we have another locker number, but this time it's to another list node. So it's going to be list node star. And then nodes. Okay, so add that here. So this is going to be 500. It's going to be 600. And finally, this last one is just going to be null. It's fine. You can have null as a locker number. Okay. All right. So this is pretty much it. And then if you want, you can also have the return. So just like the return value. Okay. So yeah, hopefully in the actual midterm, you'll just have a template for the integer and the return value. Okay, but this is basically how it's going to be. You have A, it gives you a locker number to this struct, and then same thing for B and C. So these are stored in the heap. All of these are actually stored in the heap because they were callocked. So this is all in the heap. And then these are the variables that just point to them in the heap. Okay. So that should be that, I think. So this is basically the solution that I just kind of went over. So as you can see, we have the 6 boxes for the individual variables, and then those are storing the actual items and list nodes. And I put the note here that I collapsed the strings into one box. Yeah. Would we need to include a type for the entire box? Or just each individual? Yeah. the return value would be a part of mains box, and everything else belongs to the heap. So these 6 boxes will be in main. So this is all in main, right? Whereas this is like all in the heap. I don't think you guys go too in depth into it in A48, but in B09 you'll go more into like separating variables, a memory model separating variables like between stack and heap. But yeah, I don't think you have to worry too much about that. Okay. Oops. Any other questions? Before we move on to doing some more. So for the first list node box, the name would be first, and the type is list. Yeah. First. Yeah, so here there will be 12 boxes, or I guess 13 if you include the actual return value. Or like if you want to be even more granular, you could include like the actual boxes for like first, second, and third as well. So like, yeah.
Partha, you have a question?
Yeah, so let's suppose we were using malloc instead. So would the process be the same in terms of I mean, would the memory model look something similar as to what's already there where we used calloc?
Yeah, it would look the exact same.
Okay.
Yep. Okay. So that was just like to get an understanding of the code. So hopefully now you should have a pretty good understanding of how this code works. So let's move on to doing some actual coding now. So this was a question that appeared on the 2020 midterm. So I think it's a good one to take up. So suppose you have a linked list of items that need to be rendered like this, the example that we just took up. So same thing, has a pointer to an X. This is the list node. And then the item nodes have a name and a weight. So you want to implement the insert function for the linked list of objects. The order of objects in the linked list is not relevant. So I want you guys to think of how to do this. And I want you to just give me the steps on what you would need to do. So like, give me what steps do we need to do do this function. You don't have to give me like the actual code, just the steps, and then we'll go through the code together. Okay. So I'll let you guys think about that.
Does the insert function already have a list node made, or do you have to initialize one and then link it in?
Okay. So I pressed the slide. So this is what the list node is going to look like. So you're given a head already. You're given a head list node, and you're given an item that you want to insert, and then you initially have a node that's set to null, a list node that's set to null, but you're going to be modifying this and creating like a list node out of this to allocate for this new item. So this is like what's given to you. What you want to specifically do is you want to insert this item into the linked list at the head. Okay. And if head is null, then that means the list is initially empty. So you can just create the node and then return the item. Okay. So you have to handle this situation. Don't we need to allocate memory for the new node? Yeah, that's one thing you do need to do. What else do we need to do? In fact, I guess I'll just say that that is going to be the first step. So allocate for the node. What else do we have to do? What else do we have to check? If it's not null, what specifically is not null? If the linked list is empty? You could set the next pointer of the new node to null. If you don't set it, it'll initially be null, so it's not necessary. If the head node is null, it shouldn't change anything about our function. Yeah. You don't, I mean, you don't actually need a case for the head being null. You're inserting at the front. So if head is null, you'll create the new node and then you'll let the next equal to the head, right? And so you just handle that automatically. You'll return the new head of the linked list. I guess, yeah. What you'll return is the new head of the linked list. I think I should have mentioned that here. So what do you guys think we have to do after we allocate for the node?
Arnav covered in one of his comments, he said to set the next value of the new node to the current head.
Yeah. That is one of the steps as well. What else do you think we have to do? Initialize it? Yeah, that's basically like allocating for it, right?
Oh yeah, you have to set the item to the new item.
Yeah. You have to do that too. And I'll say another thing that you have to do is actually, it's a little bit tricky, and you might, and I think you should know this, is that you should handle the out of memory case as well. So this was in the 2020 midterm. If you didn't handle this case, you lost a mark for it. So we'll talk about that. So the out of memory case, as well as after that, yeah, you do the other two things, which is set the item and the next, and then return the node. So allocate for the node, that's just, a calloc statement. Handling out of memory. So this is what happens if you set node, if you try to allocate for it and calloc gives you null, that means that you didn't have enough memory to allocate for it. So in that case, you don't actually insert anything, you just return the head. Yeah, there are part marks. So this is really important. You have to make sure that you include this part. Okay. Yeah. Oh, is this something that is only covered in Paco's lecture and not the others? Okay. It's possible then you might not need to know it. I'm not too sure. But in the previous midterm, you definitely did. So yeah, in that case, you'll be good. But other than that, like all you have to do is just set the item to new and then the next to head. And then just return the node. Yeah, so I'll re-explain it. So we're going to allocate for the node. And then we want to handle the out of memory case, right? So I won't go into it too much because, yeah, so basically like if you do calloc and then if you try to allocate for a node, for a new node, and then if calloc actually returns null, that means like you didn't have enough space, right? So like if you had like 50 boxes filled up and that was like full of capacity, and then you had no extra space, calloc would return null, which means there's no space. So because there's no space, you can't allocate for it. So you just don't do anything and you turn the head. But if Purva didn't teach it, then I don't think you have to worry too much about it.
Yeah, Partha?
Yeah, so for the list node node is null, would it be possible to do like list node equals then the line under allocate for the node all in one line?
Sorry.
So um so like the first and second line in insert item, could they just be combined in like one line and work the same way?
So if node like this first line over here, allocate for the node, if it's equal to null, return head. Is that what you're saying?
Like list node equals list node pointer calloc and that.
Oh, you mean like this first line over here?
Yeah.
Oh, this is like already given to you as like starter code, so you don't like modify it.
Okay.
Yeah. On the midterm, it was given initialized to null. Yeah. I can explain why memory leaking is bad. That's more of a BO9 question, I guess. Yeah. Or I guess Katrina can answer that. Okay. So let's move on to the next exercise. So suppose we're inserting for a new thing called compound items. So what are compound items? They basically are a struct on their own, but they have an array of items within it, and as well as the number of items in the array. So what that means is compound item is like have items. So you have some, let's say, memory address 700, and then you have like some integer like 50. So this is double star items. Sorry. Okay, and this is int, and this is n items. Okay. Excuse my messy writing there, but basically, it won't be exactly. It might not be contiguous, but like you have a list item, or you have an item, right? And this might be like 700, and then you might have another item that's like 704. So it will point to this in particular. Okay. So you can think of it like comp. You can think of it like abstractly as like comp item just has like a list of these list nodes. These these items. So like you have this is an item box, this is an item box, this is an item box. You can think of it like comp item has these inside it. Okay, and then these are like their own. They have their own name like first, second, third, etc. All right. So do you guys kind of see what I mean by what comp item is? Yeah, you could potentially have something like that. So I'll explain what we're doing here. So we're going to implement a function to insert a compound item into the linked list of objects using the insert function completed above. So the insert function completed above, that was this insert function that we just did here. So here, what we're doing is we're given a head again, but this time we're given the compound item, which includes a bunch of items inside it. And so we're going to we're going to add all the items that are inside it. We're going to go through all of them, and we're going to add continuously add them to head, and then we'll add and then we'll return the head of the new list. So basically, what that means is like, if I had something like, if I had comp item is something like this, A, B, C, and then the integer, which is just number of items, 3. And I already had like, so this is like the list node. And we have X, Y, so if I had something like that, I'm going to insert, so I'm going to take this compound item, I'm going to insert the list, or the, these are items, I'm going to insert them as new list nodes. So I'm going to insert, so I'm going to go through here, I'm going to insert A, right? I'm going to create a new list node to insert A. And I'm going to create a new list node to insert B. Oops. And then I'll create a new list node to insert C. So I'm constantly inserting at the head, basically, until I'm at the end of the list. Okay? Is that clear to everyone what we're doing here? Yeah. The thing about, I will say about Paco is that he likes to really stretch you guys in terms of like what you guys have learned in class. He'll tend to ask some questions that are a little bit outside of your scope, just to challenge you guys. He's very much into those crunchy questions. Let's just say that. Yeah. So what are some steps you guys think we have to do? Traverse through the compound item, loop through, yeah, loop through the compound item. So how are we going to loop through it? When are we going to stop the loop? How do we know to stop the loop? Yeah. So Arnav is correct. So you just basically, so the number of items is actually given to you in the comp items. So that's one way you could stop the loop. So basically, we want to loop through the n items. So these are the steps. You're going to loop through the n items. So you're going to use your for loop or while loop to do that. And then you're going to insert the item using the function that we already created. So that's just the insert item function. And then you're going to return the new head. Okay, so loop through the n items. The way you can do that is you start off at 0, and then comp item n items. So this tells you the amount of items that are going to be in this compound item. So you can set that as the actual end upper bound for the loop. And then you just simply insert the item using the function. So that's just insert item head comp items at the current I that you're on. Since this is an array of items, right? So you can index the array like this. You can do comp items I, and then you just return the head. Okay. Any questions about this one? double star. It's I++. So we're incrementing the I. The double star is just a double pointer, right? Once you, no, so you don't care about the compound items anymore. So that's for the linked list. Yeah, the linked list is not keeping track of the number of items. The number of items is only for compound item. So we're modifying the linked list. Yeah, sorry if it's confusing where you have like a linked list with items in it, and then you have a compound item with like an array of items in it. So this is different from this. Yeah, so you don't modify compound items. You modify the actual linked list, and you return the head. Okay. And like the double star thing. So, well, what do you think? A single star is just like memory address, right? Like 700. Like 1, 2, 3. Like this is 700. Like this is like if this is like I star, this is 700. And let's say the memory address is 400. Double star is just, well, it's just the memory address of this box that's storing the memory address of an integer, right? So this is going to actually be 400. So this is double star. So you can think of this as like an array of pointers, basically. So items. So this is what items will be. So items double star. It's going to be like an array of pointers. Like this. Okay, and then each individual item, this is like in this case it's an item. I should have probably picked a better name than item for the name of the struct. I don't know if it's kind of confusing. Okay. Anyways, I think let's move on to the next problem. So the next problem is when dealing with data structures, we need to clean up after we're done. So complete the function to release all the memory assigned to the objects in the linked list. So as you can see, so we don't actually need compound item here, I think. So we just need this here. So we are assigning for the item, right? And then we're also assigning for the list nodes. So this is basically the same thing as just like deleting the whole linked list. So how would we go about that? Okay. So I guess what you're given initially is you're given 2 pointers, list node P and list node Q. And so we're going to traverse through the linked list and delete the items. Okay. So I guess for the sake of time, I'll just go over this. So you should have seen this algorithm before. So basically, what we're going to do is we might have something like A, B, C. So this is just a linked list. The algorithm we have, so we're given P and Q list node pointers. So what those are going to be used for, basically, you're going to set P equal to the head that we're given. So you're given a head. You can assume that like that's the first list node. And then you're going to, so like, let's say this A is actually going to be inside an item. Okay. So this A is inside this item, and then you have next. So these are the 2 things you have. You have the item that's inside the box, the list node box, and then you have the next over here. Right? I'm just kind of representing that like that. So what you're going to do is you're going to set it p equal to q, and then you're going to let q equal to p dot next. And the reason why you're going to do that is since we're freeing up the memory, what will happen is you're going to free up this item, and then you're going to free up this list node. But then all of a sudden, if you don't keep track of what the next is, you're not going to know, you're not going to be able to go to the next item, right? So that's why you need to use the second list node pointer to iterate through. So you're just going to go through that. And then after you're done, you've cleared out what's in P, you're going to go to Q. Okay, and then you're going to do the same thing. You're going to keep track of the next, then you're going to free these, and then you're going to continue on until eventually you free everything, and then P is equal to null. Okay, so that's what that's going to look like. So I'll just explain these steps. So you guys should have seen this algorithm in your tutorial. So it shouldn't be too difficult. You start at P at the head. You loop through the nodes in the list. So you just do like while P is not equal to null. Yeah, that looks pretty close. Yeah, that looks pretty close. I think you're missing one thing. Keep track of the next, free the item in the node, and then increment the pointer. Yeah, you have to free the item. That's the only thing you're missing, Minjun. So P equals head, while P doesn't equal null, Q equal P next, and then you free the item first, and then you free P, and then you free P equals Q. Okay? Because the item, it's going to be allocated in the heap. So like P is allocated in the heap, and item is allocated in the heap as well. So they're allocated in different parts of the heap. And so you need to free both of them. Yeah. Okay. So let's move on to some complexity. So we'll hopefully get through this pretty quickly. So suppose you have a linked list of items that need to be rendered. So again, like the same linked list that we had before. And let's say now we care about order. Okay. And let's say we care about like, with respect to name. Okay. We want it to be like alphabetically sorted. Okay. And you're trying to remake the insert function. And you want to insert a new item into the linked list while preserving the order. So that means that, you know, if you have your like ABC, or like maybe we can change this to like AB. If you were to insert C, you'd have to go through the linked list and then try to preserve the order. You want to make sure you insert it here. Okay. So you no longer want to just insert it at the head. You want to check the actual position that it needs to be entered. Okay. So the questions are, what is the big O best case complexity of inserting a single object into the sorted list? And also, in what situation would we have that? O of 1? Yeah. So if you want to insert, and it's the first item. Exactly. Yeah. So it's O of 1 if you want to just insert at the start of the list. Okay. Insert at an empty list. Yeah. So that's basically the same thing as like inserting at the start of the list. What's the worst case complexity? When would this happen? O of n? O of n? Yeah. So basically, O of n, where n is equal to the number of items in the list. Worst case scenario is if it's inserted at the end of the list. Okay. And average is n over 2. Yeah, exactly. So average case complexity is, you know, you insert like roughly in the middle of the list, n over 2. But of course, the important thing to know is that constants don't matter. So it will simplify down to O of n. So O of n, where n is the number of items in the list. So on average, you will need to scan through n over 2 items, like you guys mentioned. So it would be O 1/2 times n, but 1/2 is a constant, and the main dominating factor is this n here. So it will still be O of n. All right. Make sense? Yeah. All right. Let's move on to the next problem. So let's say we still want to preserve order with respect to some property like item name, so same as before, but we're given an unordered list, and we want to sort the unordered list. So I want you guys to try to describe an approach you could use to sort the list, and then what is the big O worst case complexity of sorting the linked list. So I want you guys to think about this. Quick sort. So like more specifically, like explain how it would work. So I'm not sure if you guys went into the details of how quicksort worked just yet. Select a random pivot. Yeah, I don't think quicksort would even work because this is a linked list, and quicksort you need indices. You don't have the indices. Bubble sort. Yeah, so how does bubble sort work? Can someone explain it to me? How does bubble sort work? Bubble an item with the largest value to the end. Compare the ith with the I plus 1. And move it up. Yeah, exactly. Yeah, and just repeat that for every single item. And what would the complexity of something like that be? N squared? Yeah. Yeah. So, yeah, bubble sort is absolutely one approach you can use. So what bubble sort is basically for each node, you check if its name comes later in the alphabet than its neighbor. So that's like checking if you have a one item, the item dash next, if it's greater, then it'll push it, and then it'll repeat it until it's at the right position, and then repeat it for the rest of the nodes. Okay, so that's bubble sort. There's other types of sorts as well. So you can have like insertion and heap sort as well, but you haven't learned those. So like, yeah, bubble sort is fine. And this is going to be n squared complexity. And you can do n log n with like heap sort and merge sort. So I think merge sort might not be possible, but like you don't have to worry about that. However, I do think you can actually use heap sort here, but I don't think you learned about that yet. So you don't have to worry about that. It's just that if you look at the Unit 4 slides, you'll see that it does mention heap sort as like an n log n algorithm you could use. And that would work here, but bubble sort is fine as well. Okay. And if you want an explanation for why bubble sort is n squared, so basically, so you have unordered list. So the reason why it's n squared is because you're going to have 2 pointers, like let's say P and Q. You're going to see that D and B are in the wrong position, so you're going to swap them. And then you're going to continue to, so now you're going to, your P is here, your Q is here. You're going to swap the D and C again because you see it's in the wrong position. Oops. So you're going through this. You're going through this process n times, right? N is like the length of the whole linked list, right? And now finally we see that D is in the position. Okay, and then what you do is you're not done, right? It's still not sorted. you have to start this process all over again now with the first item in the list. Yeah. Actually, yeah, you actually need 3 pointers. You need a previous, a cur, and a next. So like the reason why is because for linked list only, when you modify like current item, like let's say this one, right? You have to do, okay, a good example. Okay, let's say for this one, right? For C, if you want to swap it here, you need to change B's next equal to A, right? And you also have to make, so like you need to keep track of the previous as well. So that's why you need 3 nodes or 3 pointers for this one. But you don't have to like it doesn't specifically say like you have to write the actual code for it. It's just give a general approach and time complexity. But if you want to know how you'd actually implement bubble sort, I do believe you need 3 pointers. You can copy the data. Yeah, I mean, technically you would get the same solution for that, but I think it wants you to swap the nodes instead. Okay. But yeah, I think yeah, that would use more memory. Yeah. So like you don't have to go like too into so you don't have to go too into the specifics for this question. It's just like what is the general approach and what is the time complexity. Okay. So yeah, that's pretty much it. Since we had time, I decided to go a little bit slower. So we still have some time for questions. So yeah, we have like 20 more minutes. We can just hang out and whatever questions you have, we'll try to answer it. Do we have to know how to compute log n stuff? I'm not. So like you might need to know like how binary search works. But you don't need to know how like the more complicated sorts works just yet. Okay. I think yeah, you don't need to know about like heaps, like how heap sort works specifically. It's just mentioned in the notes because you are like early into complexity. The n log n sort we talked about was quicksort. Yeah, quicksort is interesting because worst case quicksort is actually not n log n, and you'll learn why that is. On average, it's n log n, and it's only if you pick a good pivot. Okay, but we won't get too much into that. Yeah, worst case is n squared. What time is the midterm? I don't remember. Check the Piazza post. Yeah. Yeah, bogus sort. Okay, somebody said the double star thing. Okay. Let me just type.
Yeah, Arnav, you're correct. So like that first star, basically you have an array of pointers, and then so the double star, the int num addresses, is just pointing to the first, I guess, pointer in the array. And then the array has several different pointers. So in the example that Tabeeb's doing, nums1, nums2, nums3, they're all pointers, but now they're in this array, right? And then that array, like each of the pointers also points to its own individual integers. Pointer, which is pointing to an int pointer. Yeah, kind of. Like that's the complicated way of thinking about it. Yeah, I mean, yeah, basically, you're pointing to a pointer for the first like object in the array, which is a pointer pointing to an integer. Yeah, basically, but it's a bit difficult to visualize. In this case, I don't think you would need the brackets. Like, why would you need the brackets for? Or what would the brackets be for? Oh, I see. That would be casting it. That would be typecasting it to an integer pointer. Tabeeb, you having fun there?
Yeah. Ooh. I think I need a break. I've been going at it for more than an hour.
You did really well. I'm sorry I went fast.
Oh, you're fine. You guys will be fine.
Yeah, just a reminder, just make sure when you're referencing like compound data types that you create, if you're referencing it, the example I gave, review rev, if it's the actual data type, then make sure that you use periods or dots versus like a pointer. Then you want to use the arrow.